Hi. All right. Sure.
Hello, Hector.
Hi, how are you?
Good.
Yeah, fine. I'll just be quiet.
Okay.
I'm glad you two know each other. Okay, so let's get started. Do you have any questions on anything? All right, so to continue with where we left off last time. So last time, right, we were discussing the trace determinant plan. This is section 3.7, by the way, right? Or it's also known as the bifurcation for 2x2 system. Okay. And so the example we want to keep in mind, or one of the example we did, right, is the following. So y prime equals to a times y, where a, right, depends on a parameter, little a, okay? So the main question we want to ask is, right, find the values of a, right, so that the behavior of the solution changes, right, significantly. I guess find the values, right, so that the behavior of the solution changed significantly as a, right, cross these values. Okay. And of course, right, this is like the bifurcation that we looked at in the one-dimensional case, where, for example, you could have, like sink change to source, right? Spiral sink, spiral change to non-spiral, that kind of thing, right? Behavior in terms of the equilibrium solution. Okay. And the technique, right? The technique that the strategy that we employ in doing this question is to first, right, plot the, well, TD point, right? First, you plot the TD point and you pay attention, right, to the important boundaries, TD, right? You pay attention to the following important boundaries. Right, this is the parabola where, let me see, right, t squared is equal to 4d, right? That's the first one that you pay attention to. The second one, right, is the upper half, right, the positive v axis. And the last one, right, is the t axis, all right? These three are the boundaries, the important boundaries that you want to pay attention to. So A, right, you do this. B, right, you plot the curve, plot the TD curve, right, given, right, as a, as a parametric curve. Right, depending on A. the TD curve of the matrix A, all right? The TD curve of the matrix A. In other words, right, because there's a parameter A here, right? The trace of A, right? The trace of A will be a function of A, right? Function of little a. The determinant of A will be a function of little a, right? You plot these two D, right? These two together on this plane, right? On this plane. For example, as you remember, for that particular example we looked at, right? The curve will be a straight line, okay? We'll revisit that. And then C, right? Look at, right? Identify, right? The intersections, right? Of the TD curve, right? With the, let me say, critical boundaries. Okay, there are three boundaries in total: the parabola, right? The positive b-axis, and the t-axis. Okay, these, right? And we'll go back and review. But basically, you see each of these regions, okay, denote a different, right, behavior of the the equilibrium solution. So that's why, right, as your curve crosses, right, these boundaries, you transition from one region to another. And that's why the behavior, right, of the solution changes in terms of the quality, right, the qualitative behavior of the critical of the equilibrium solution changes. And so identify these the intersections, right? These will be your, these are the bifurcation values. All right. So again, right, we'll go back to this graph and spell out the regions just so that you get the idea in mind. In terms of the practicality, you see, if you just want to find the bifurcation values, then as long as you remember these regions, right, you don't have to kind of work out what kind of behavior in each of the regions. But I think it's good that you can do so. Okay, so we'll review that. But just to demonstrate, right, the technique here, the matrix that we looked at, right? So in our example, the matrix A is minus 2A minus 2, 0. Right? So the trace as a function of A, right, actually is just a constant minus 2. Trace is a sum, right, of diagonal entries. The determinant, right, is going to be 2A. Okay. So now you plot, right, you plot this as a parametric curve, which is quite easy here on the trace determinant plane, right? Minus 2. So this is, right, this is the line. This is the parametric curve, t equals minus 2. Okay. So from that point of view, right, we have two intersections here and here. All right. So you see that you have two bifurcation values. Right. The first one is the intersection, right, with the parabola. And don't forget, right, what are we solving for? We're solving for the value of little a, right? That is the critical value for the bifurcation. So you want to, right, translate, again, the language of the trace determinant back to the a, right? So what do we have? The parabola, right? The parabola is t squared equals to 4d, okay? So if you're on the parabola, that means that these guys also satisfy the equation of the parabola. So in other words, right, you got 4 is equal to 8a. So here a is 1/2. Okay. The second one, right, is the intersection with the t-axis, right? So intersection with the t-axis means d equal to 0, right? But d equal to 0 means a equal to 0. So your two bifurcation values are 1/2, a equals to 1/2, and a equal to 0. Okay. Any question on this? All right. So I want to do a quick review, right, on the regions, right, that the TD, right, the TD regions, okay, according on how it's divided by the parabola, by the critical boundaries. So remember, right, where do we get this from? If we consider a general matrix A, right, which is A, B, C, D, and we look at the characteristic equation, right, which is A minus lambda times D minus lambda minus B times C equal to 0. This translates to lambda square, right, minus A plus D lambda, and then plus AD minus BC equals to 0, or lambda minus, right, A plus D is a trace, and AD minus BC is determinant equal to 0. And so you see, right, the solution, the eigenvalues, right, can be expressed as t plus minus square root of t squared minus 4d over 2. Okay. And so, right, above the parabola, right, you see the parabola is where t squared minus 4d is equal to 0, right? Above the parabola is where t squared minus 4d is negative, right? And below the parabola is where t squared minus 4d is positive, okay? And that explains why, right? The parabola is a critical boundary, because as you cross the parabola, right, you're crossing between the real solution into complex solution. Okay, so that explains this. Okay, second, right, what does it have to do with the sign of t then? What does t control, right? T, right, controls the, well, you know, the sink or source behavior, right? Because basically our solution, right, how do I want to say this? The solution, right, if so, the solution, roughly speaking, right, your solution to a system is y of t, right, is v1 e to lambda 1t plus v2 e to lambda 2t, right, where lambda 1 and lambda 2 are the eigenvalues, these two eigenvalues, right, and v1, v2 are the eigenvectors, okay? So you can see that either way. For example, that if this is negative, right, you're above the parabola when this is complex, then the sign of t, right, control whether it's spiral sink or spiral source, all right? So the sign of t, if t is negative, that's going to be spiral sink. If t is positive, it's going to be spiral source. So in other words, right, crossing this right here, right, crossing this right here changes, right, the behavior. So I just said, right, this, we concluded this is spiral sink and this is spiral source. Is that okay? Right, because right? If this is a complex part, then this is the, this is the sign, right, of the exponential, right? That controls the decay or the growth of the solution, okay? And that explains why, right, crossing this changes the behavior of the solution, right? So changing here, change from, complex to real solution, but changing here, right, changing from sink to source. Finally, right, what happens when we cross this? When we cross this? Well, that has to do with, right, the sign of D, right, the sign of D. Well, if you remember, right, so if you're below the parabola, then basically all the solutions are real. All the solutions are real, right? All the eigenvalues are real. So from that point of view, what you worry about is whether, right, the sign of the two eigenvalues, is it the same or opposite? Okay, because, right, if they're opposite, then the equilibrium, the equilibrium solution, right, becomes a saddle point. Okay, and how do we decide that? Well, to check the sign of the two eigenvalues, right, basically we just have to multiply them together. So if you multiply these two together, lambda 1 times lambda 2, right, will be what? You got, right, basically a minus b times a plus b is a squared minus b squared. So you got t squared, right, minus. And by the way, when we're below the parabola, right, we're looking at when we're below the parabola, we assume that t squared minus 40 is positive, right? That's what it means to be below the parabola, because above the parabola, we already consider that to be a spiral. So below the parabola, I guess, is what we're looking at, right? Below the parabola, where t squared minus 40 is positive, okay? So all real eigenvalues. Then this is going to be t squared minus 40, right, divided by 4, which is, just d. So, right, that explains to us that if d is negative, right, if d is negative, this and this are both saddle point. Okay, they're both saddle. That's why the negative part of the d, when you cross it, it doesn't change the behavior because it's still a saddle point anyway. All right, so you only consider the positive part of the axis. All right, finally, right, what is this and this? Well, you see that if d is positive, okay, if d is positive, then the eigenvalues have the same sign, either both positive or both negative. So we just have to look at, right, the sign of one of them to decide the sign of the other. So if on this part, that means that t is positive, right? If t is positive, then at least the plus solution is positive. That means that this is going to be just your source. Hold on, right? Sorry, I made a mistake. Here t is positive, so it's a spiral source, right? I apologize. This is spiral sink. I apologize because t is positive here, right? T is positive on this side, so it's going to go out. So a spiral source. This is spiral sink. Okay, so this is just going to be source. This is going to be sink. Okay. So all in all, right, this is a good exercise for us to name, right, these regions where there's a significant change in the quality of the equilibrium solution, right, as we crosses these boundaries. But as far as practical, right, approach is concerned, you only have to remember that these together, right, the red, the highlighted part, are the ones you want to watch out for as the TD curve of your matrix, right, cross that, okay, cross them. Question on this? Okay. So I guess we're just going to do a few more examples, right, to show you the technique and kind of show the variation of how you will approach this problem. So let's look at problem, so look at problem 2. I think it's too easy, but doesn't matter. So y prime equals to ay in from all of these. A is a minus 1, 2, 0. Okay. So here, right, so first you want to find the trace and determinant of this matrix as a function of a, of little a. So what's t? T is a, right? D is 2. Okay. So now you plot this, right, on the TD curve. Sorry, on the TD plane, right? How does this look? How does this look as a curve, as a parametric curve on this TD plane? What does it look like? Correct, right? Exactly, a horizontal line. So how many bifurcation points do you see, Carl? How many bifurcations do we have here? Correct, right? 3 bifurcations. All right. What is this value here? What is a equal? Not to Mohammed. I'm not sure if you're missing this one, right? This one is also a bifurcation because remember, this is exactly changing from sink to source. So yes, right, that's also bifurcation. So what is a equal here for this? How do you find that? Actually, let's see, right? Maybe this is easier here. What is a equal to here for this one? Okay, I got square root of 8 here. Let's see if that's true. All right. Well, how do you find that? Well, so let's call this point 1, right? 2 and 3. So for point 1, right, you're on the parabola, right? And the parabola is what? The parabola is t squared equals to 4d, right? T squared equals to 4d. Now, so t squared is a squared, and 4d is 8. So exactly 8 is, right, square root of 8. But hold on, right? So Daniel, why is it that a is positive here? And why is it not negative? How do you know? It doesn't matter, right? Because you intuitively, maybe one of these is minus, one of these is plus. How do you know that one is a positive one? Because, right, exactly, the trace is a, right? So here, this point has t positive, right, as part of it. Do you agree? The difference between point 1 and point 3, right, is point 1 is t positive. Agree? So exactly, right? So again, right, I guess when you, if the point just to find all bifurcations, then I guess when you write this, it's not easy to fault you, but you're not getting the whole picture, right? If you don't like kind of distinguish that here, right? Because t is positive here. Okay. Yeah, that's right. Any question here on this? What about 2? I guess 2 is too easy, right? T as a trace, Saga, right? T as a trace. T as a trace. What's the trace of this matrix? Or I don't know. I mean, you're asking why t is positive here because you're right here, right? This is a positive part of t. Okay. And if you ask why a is positive, because here trace is equal to a. All right. So yes, right. The second part is exactly a equal to 0. Because right, that's exactly t equal to 0 there. And the third part is, I think it's obvious, right? The third part is a is minus root 8, right? Are we okay? Any question? All right, so let's take a look at the next one. We're just going to do like a few interesting questions and that's it. Let's look at 3, right? So here the matrix is a squared plus a, 1, and a. All right. So again, right, step 1, you look at the trace and you look at determinant. Trace is 2a. Determinant is a squared minus a squared plus a equals to minus a. So then you plot the trace determinant plane. And then you have your parabola. Okay. So how does this curve look like on the trace determinant plane? What does it look like? This is from Calc 3, right? This is exactly where a parametric curve enters. So you want to, right, kind of solve for d as a function of t, right? And I think it's clear that d here is minus 1/2 t. Yes, d is minus 1/2 t. So therefore, right, it's going to be a line with slope minus 1/2, like that. Okay. So how many bifurcation values do we see? 2, right? Exactly. Here and here. So I think this point is easy. I'll do it for you, right? This is a equal to 0. What about this point? What is the value at the first one? What is a on the first one? So there, I guess, right, there are several approaches, but you realize it's the intersection of the parabola with the line, right? So I guess you have, I don't know, t squared equals to 4d, right, as a parabola. And then you also have, right, d equals to minus 1/2 t, right, like that. So if you want to plug in right there, then you got, right, so t squared equals to, if you plug this in here, right, it's going to be minus 2t, right? So you got t squared plus 2t equals to 0, or t equal to 0, which is, right, obviously this point, or t equals to minus 2, which is obviously this point. And if t is equal to minus 2, then what's a? Minus 1. right? Okay, we got a hang of this. One more question, one more example, or this is enough? Oh, sure, right? So see here, Carl, right? T equals to -2 and T equal to 0, right? As I solve for this, basically this is what? This is the intersections of the line and the parabola. Now, T equal to 0 clearly corresponds to this. T equals to -2 corresponds to this. And then I go back to see what is A, right? What is T in terms of A? And I solve for A. We're assuming that A, B, C, D are all real. Yeah, you mean like the matrix? Yes, the matrix are real valued, right? The matrix are real value matrix, yes. Because otherwise, right, the eigenvalue itself can be complex, right? And I mean, how do I say this, right? Does that affect anything here? Does that affect anything here? I think it does, because, you know, Daniel, right? Part of the analysis that we did relies on this part right here, right? Remember, we said t squared minus 40 is positive and t squared minus 40 positive, right? If we don't assume real value, then the analysis goes very differently, right? Then the square root here doesn't have that kind of interpretation anymore, right? Yeah, except that, right, there is not going to be just T and D. You see, right? It will depend on one more thing, and I don't know what that is. And the analysis, right, there would be more complex, because then you have to characterize the cubic root, right, in terms of their sign, in terms of their complexity, that kind of thing. You can, but I think there it will be quite demanding in terms of the analysis. All right, so I think I just want to do one more, problem 5, because again, it looks interesting. A is A square root of 1 minus A squared, 1 and 0. All right. So again, right, so here T is A and D is square root of 1 minus A squared, I think with a minus. All right. This looks interesting, maybe. So the TD plane, how does this curve look in terms of a TD plane? Oh, and by the way, right, because I guess goes to what Daniel was asking. Here we want A to be between -1 and 1, so that this is real value, right? So we have that restriction. How does this curve look in terms of the TD in terms of TD plane? What is it? Semicircle where? Which semicircle? Right. Exactly. So it's going to be this. Right, Daniel, but remember, right, because of this and the square root, it's a semicircle, right? It's not going to be the full circle. Mm-hmm. All right, so is there any bifurcation in this case? Okay. Any bifurcation? Which one? You mean here? I don't think it's a bifurcation. You know why? Because what's the region down here? Right? The region down here is always saddle point. So I think crossing here won't cause a bifurcation. All right. So does that mean there's no bifurcation here? I think I would check this too. Right? Because I think it's allowed that you're equal. You're equal. All right. You're equal here. So it's possible, right, that, okay, so here, what is special about this one? Exactly. What is special about this one? Do you remember? If on this line, what happens? What happens on this line? And tell me the behavior of the solution on this line. Well, saddle is down here. No, center is right here. Center is up here, complex. Read it. Exactly, repeated eigenvalue. Repeated eigenvalue because, oh, no, Songy, no, not really. Not really repeated eigenvalue. What is this actually? What is the special value here? Do you see that this is d equal to 0 on this line? No, t equal to 0 is here, Daniel. Right? The curve is right here. You understand? Yeah, you got to pay attention, right? T equal to 0 is here, which we say, right, doesn't change the bifurcation because they're both it's always correct. Exactly. D equal to 0 gives you a 0 eigenvalue. And what's special about 0 eigenvalue? What's the number one behavior of 0 eigenvalue that makes the quality very different? Infinitely many equilibrium solutions. Yeah. Why? Because the solution, right, ay equal to 0, when a is not invertible, has non-zero solution. Okay. And so before, right, when determinant is non-zero, you always have, right, this matrix being invertible. So the only equilibrium value, the only equilibrium solution is y equal to 0. But when determinant equal to 0 or a is not invertible, then you have non-zero solution. And automatically you have infinitely many equilibrium solutions because then, right, any constant times this is also a solution. Okay. So in other words, right, anywhere else down here, you only have one equilibrium solution, y equal to 0. Right here, you have infinitely many equilibrium solutions. So, right, that would be a qualitative change. So I would say, right here, lambda equals to plus minus 1 are bifurcations. Is that okay? Any question on this? Oh, sorry. I mean A, right? I mean A, because really, right, this is, hold on. Yeah, I mean A, because, sorry, I wrote it wrong. T, right? This is T equals to plus minus 1. But of course, right, T equals to A, so A equals to plus minus 1. Yeah. Are we okay? So, right, I mean, like, I hope these examples, the bifurcation, because you go from infinitely many equilibrium solutions to one equilibrium solution, which is a saddle point. And then one equilibrium solution, which is saddle point, back to infinitely many equilibrium solutions. And that's a change. So that's bifurcation. Okay, Saga? All right, okay. So I hope these examples demonstrated what don't you get? So the curve, right, runs, I don't know, from -1 to 1, so it runs from here to here. Okay. So when lambda goes to, when A goes to -1, this is here. All right. How does the system behave? That's D equal to 0, and you have infinitely many equilibrium solutions. And then when you go down here, you only have one equilibrium solution. And then when you go back up here, you have infinitely many equilibrium solutions. In my opinion, right, that's a change in terms of the qualitative behavior of the system. Actually, remember the graph, right? The graph of saddle point versus the graph of, zero eigenvalues are very different. So you can look at that. That alone tells you that, these are very different kind of behavior. So that's the bifurcation right there. Okay. Any other question? All right, so this is all I want to say about the TD plane, all right, about this section. The next one is 3.7. The matrix called, three-dimensional system. Sorry, the textbook called it the three-dimensional system. I'll skip. All right. The reason is basically what they do is they talk about classification of equilibrium. Solution, for 3x3 system. I think some of you asked this before, right? And I guess Daniel even also asked today about, can you generalize, right, what we did in 2x2 into 3x3 and above? And so here 3.7 says that you can do it up to a point, basically by analyzing, the sign of three eigenvalues together and see how the three eigenvalues interact. But basically, there are too many cases. There's too many small cases that I'm not super interested in. Like it makes sense. You can basically still say there's a sink, there's a source, that kind of thing. But there are basically too many small subcases that I'm not super interested in. So if you want to and you're interested in this kind of topic, you can read it by yourself, right? I think there are more like other topics that we can cover, we can focus on. So we'll skip this, all right? It's a generalization of what we did for the 2x2, but not in a very nice way, because you cannot say precisely what's happening anyway. Like you just have to break it down to really small cases, and I'm not interested in that. Okay, so the next section I want to talk about is 4.1, and for that matter, it's going to be 4.1, 4. Chapter 4 in general. And this is going to be, roughly speaking, what we look at as non-homogeneous, non-homogeneous second order linear ODE with application to, let's say, spring mass system. Doesn't have to be spring mass, right? I think someone mentioned RLC system, but I'm not very good with electromagnetic, so I'll skip that, right? I'll just talk about the interpretation in terms of like the spring mass system, right? But so what's the general idea here, right? First of all, the general idea is we have a second order linear ODE. So in other words, right, we have this system, this equation, AY prime plus AY double prime plus BY prime plus CY, okay? Before we looked at this, right, equal to 0, that's homogeneous, right? Non-homogeneous means you have a function, let's call it f of t, okay? And so basically chapter 4 discusses how to solve this kind of equation for different types of f of t, okay, on the right hand side. So we'll talk about that. But the application, right, is exactly, remember when we have this my double prime, right, plus I think it's called by prime plus ky, right, is equal to f of t. So in the context of spring mass system, right, m is the mass, b is a damping constant, right, k is a spring constant, right? So actually we discussed this, right, last time, and I said I think I told you something not correct there, right? I said we will not look at the case where there's a forcing function. We do, right? Actually, I forgot about that. So we will look at the case where there's a forcing function. So f of t here, right, is viewed as the external force, right? External force that actually depends on time, okay? And you can see actually the interesting case is when this is going to be a cosine sine function whose frequency, right, coincides with the natural frequency of the system, which will cause the phenomenon called resonance, right, which we'll discuss on 4.3. So that's the application for this kind of equation. But so the mathematical content is we'll learn how to solve this in general, not in general, but like for some forms, right, for some forms of f of t. And then we apply that to the interpretation of the spring mass system or the RLC system if you want to cast it into that model. So 4.1, okay? Actually 4.1 is when they look at f of t as e to the, let's say this, e to the alpha t like this, or f of t is equal to some polynomial in t. And then 4.2 is when f of t is cosine, alpha t or sine, like that. So basically, I think so, Daniel. I am not sure. Can anyone comment on that? Is some external force besides your circuit, right? I think your circuit has RLC set up. So there's some outside component that kind of interact with your system in some way. So probably, yeah, it sounds right, but I cannot confirm 100%. Could be some some other things that interact with your system. I'm not sure, electromotive or whatever that is. Okay, so what is the general principle, right? What's the general principle? When we solve for this kind of system, right? The general principle we will have looked at before is, first of all, you solve for the homogeneous equation solution. YH of t, where YH solves AY double prime plus BY prime plus CY is equal to 0. Okay. And B is to guess, right, for a particular solution. To the non-homogeneous equation. YP, right? We call it YP. And so, right, of course, the guess here is not just like purely guessing. There's a method to it, and the method is called the method of undetermined coefficient. Right. Again, we have looked at this, right, in the the first order equation case. Now we just do it for second order. And C, right, your general solution will be YH plus YP. Okay, like that. So I think it's easiest just to look at an example. All right, so the example here says y double prime plus 5y prime plus 6y is equal to eta minus t. All right. So first, right, you solve for the homogeneous equation. So equal to 0. And of course, right, you look at the characteristic equation. And easily you got lambda equals to -2 and lambda equals to -3, right, are solutions. And so your homogeneous solution will be C1 eta minus 2t plus C2 eta minus 3t. Is this okay? So 2, right? What is the guess for YP? So the method on undetermined coefficients, right, involve guessing the right form for this guy, right? You leave a coefficient to be undetermined, and then you solve for that, right? So that's called the method in the undetermined coefficient. So does anyone remember what the guess for this guy is? It's the same exact principle as the first order equation that we talked about. Correct, a to e minus t, correct. Right, and then you plug in and solve for a. So plug in, right? Well, fortunately, right, this is easy. You got a, so y double prime, right? It's just a to e to t, e to minus t, right? Because you do it twice, you got just that. 2 minuses becomes a plus. And then the y prime is minus 5a, right? And then y is plus 6a. Right, is equal to eta minus t. So in other words, right, you got 2a should be equals to 1, or a is equal to 1/2. Right? And so your solution then is C1 eta minus t plus C2 eta minus 3t plus 1/2 eta minus t. Okay, question here. So simple and straightforward, right? Let's change it. Let's say y double prime plus 5y prime plus 6y is e to the minus 3t. Did I do something wrong? Oh yeah, thank you. I missed this. Thank you. Yeah. All right. So now I repeat the same question, right? Changing the right-hand side, the forcing function, right? So remember, yh of t is c1 e to minus 2t plus c2 e to minus 3t. What's the guess for my yp? What's the guess for my yp? You mean 2t, right? Minus, I mean, you mean minus 3t, right, Will? Yeah, correct. And exactly, right? Will saw the key point, but I guess missed the other one, right? So why this and not yp equals to a e to minus 3t? Right, we talked about this before, right? This form would not work in this case because it exactly, right, coincides with the homogeneous solution. So if you plug this into the equation, you will get 0. All right, you get 0. So there's no way you can match it with the right-hand side. Okay, so right, because here, right, this one coincides with YH. All right, and so right, the principle of method undetermined coefficient is you multiply with the smallest power of t, so that right your guess does not coincide with the with the homogeneous solution. All right. So for that matter, right, we have, so now you plug in, right? So here plugging is a little bit, I guess we need to keep track of things, right? So yp is at e to minus 3t. Yp prime, right, is going to be, well, so first you have a e to minus 3t and then minus 3, right? At e to minus 3t. Okay. And then yp double prime will be, right? So you got minus 3a e to minus 3t. Okay. And then you got another minus 3a, right, from differentiating this. So you got minus 6a. And then differentiate the other one gives you 9, right? At e to minus 3t. Okay. So, I mean, you could plug everything in, but as a matter of fact, right? When you plug in, guess what happens to these 3 terms? Guess what happens to these 3 terms? Exactly, right? If you do it correctly, they should cancel out. So you can do a mental check that they cancel out. Why should they cancel out? Because your right-hand side do not have them, right? If somehow they don't cancel out, you're in big trouble. So they do cancel out, right? These 3 terms. So you don't have to write them out, but just do a mental check, right? What's the mental check? 9 minus 15 plus 6 is indeed 0, right? 9 minus 15 plus 6 is indeed 0. So fine, right? I just have to do the other case, which is minus 6a. And then I have here, right, this, which is 5a. which is equal to 1, or a is minus 1. Is that okay? Any question? All right, let's do the next example. Let's say this, y double prime plus 4y prime plus 4y is e to a t. What, Sagar? Did I miss something? Why 1/5? This is minus a equals to 1. So a is minus 1, right? Okay, so let's do this question, right? What? So second derivative is minus 6, but the first derivative is 5. So you got minus 6 plus 5. Anyone else see that I did something wrong, or? Okay, if someone else see I did something wrong, just spell out. Otherwise, I think I'm okay. And Sagar made some mistake. So here, right, in this one, if you look at the homogeneous, you got lambda squared plus 4 lambda plus 4 equal to 0, or lambda equals to minus 2, right? Repeating. Okay. So what is the homogeneous solution here? Homogeneous solution, right, is eta minus 2t, t eta minus 2t. All right. And so your yp, right, is a e to a t. I hope that's not shocking to anyone, right? A e to a t, that's fine. And then you solve for a. I'll skip that. Right, that's easy. Now, but what about this case? Well, this case, right, where your YH is like this. What should your YP be? You have an extra minus. Oh, no, my fault. And you understand what I'm saying. If it's this, then there's no minus. You understand what I'm saying too. I'm sorry. I meant the minus there. Thanks, Will. Yep. And then exactly, right? Sorry, I mean the minus here, right? And yes, so it's going to be t squared, right? Eta minus 2t. With an a in front. Okay. Anyone have a question about this? No, Will, because what is the integrating factor method, or what does it rely on? What's the basis behind integrating factor method? The idea behind integrating factor is that you have something like this. Let me say, okay. So py prime plus qy, okay, is going to be something like integrating factor y prime by product rule. Okay, so in other words, product rule is the key to integrating factor method in 1D, in first order equation. Can you imagine a product rule for a second derivative operator? I mean, not that you cannot, it's just that I'm not aware of one that can be easily fit into this to begin with, right? You understand what I'm trying to say? So here, right, if you try to fit into this bill, then you're looking for something, I don't know if like this, you're imagining something like this, but it should not work to begin with if you check the form out, I think, okay? So that simply that basically you don't have the product rule in this way for the second, for the second order derivative. So you don't have that. That being said, right, there is a method called the variation of parameter. Again, I'm not so sure if if we'll cover that in this class. I don't think we cover it in 244, and you can look it up, on the web to see what they talk about. I'm not sure if it has the flavor of the integrating factor approach to begin with. All right, but there is another way to dealing with this that is a little bit more general than just guessing the form. And finally, all right, since you mentioned integrating factor, right, that means you like first order approach. If you like first order approach, can you see what you could do to this equation to make it first order? No. What substitute for what? Oh yeah, exactly. You can change the system, exactly. You can change it to first order non-homogeneous system. And right, and exactly, this is, then you remember, so you got y prime equals to ay plus some f of t. Okay, and our first step, right, of talking about how we define something like this could be the first step, right? And you see exactly here is where the value of having the exponential matrix, the matrix exponential, as a mathematical tool, right, to start discussing about something like this in a more general way. Is that okay? That's what we was asking. Now, I don't know, okay, on top of my head, how to generalize, like let's say the integrating factor technique or whatever that is to the system of first order equation. But right, I mean, like, at least, you could kind of visualize that once you translate it to a first order system like this, where the notion of the exponential also applies, okay, also is defined as we showed before, then you can also do something with the case when it's non-homogeneous. All right, now the right way to develop that, you have to think about, or I haven't really spent time, right, looking for the way, but you can see that that's exactly the value of us translating it to this formulation. Okay, yeah. So, all right, so, okay, back to reality. So here, right, we're discussing method of undetermined coefficient, and this is the right guess, all right, for this equation. Now, why is this the right guess? Because if you were to only guess with one single t, right, then it won't work because it coincides, right, with this. Right, without T, then it's even worse, right, because it coincides with this. Now, I want to do another one. But I want to do this. Okay, with the T in front. So remember, YH is C1 e to minus 2t plus C2 t e to minus 2t. I don't think the textbook goes this far, but anyone care to guess what the YPT, what the form for the particular solution here is? You appreciate this question, right? Because before, when I asked just e to minus 2t, then Will said, right, you have to multiply by t squared to get out of the homogeneous solution. Now I changed this to t, okay? And I ask, what is the form of the non-homogeneous, of the particular solution here? Will completely incorrect because both of those are homogeneous solutions, right? I don't see any square in there even. What you wrote there is just another reiteration of what I wrote, which is a homogeneous solution. I'm asking for the particular form, right? Haha. All right, I was waiting for someone to say that. But Daniel, right? Think about it like this. This is your guess. This was Will's guess. Any difference? But are the right-hand side the same? Right. So one of you would be right and one of you would be wrong. And I guess I said Will is right. Yeah. Roughly yes, but what is that plus a term? Correct. You have to go to cubic here. Okay, so the way you look at it like this, and this it's a little bit strange. Okay, first of all, you look at this as a generic. Okay, you look at this as a generic linear function times e to minus 2t. Is that okay? This is just matching this with this without caring for the homogeneous solution yet. Are we okay? This is just matching like this. But this is exactly what Will wrote, all right? And that lands us exactly right here. So the principles say I have to multiply with the smallest power of t. Let's say this. I don't know what thing I want to use. T to the n, t to the k. The smallest k, so that nothing here coincides with my homogeneous solution. What k would do the trick? What k would do the trick? Correct. K equals to 2. Because if k equals to 1, right, then this will get out, but this will still be in my homogeneous solution. So, okay, so k smallest. So YH, so YP has no coincidence, right? Coincidence. with YH. And so here K equals to 2. And so you got T squared AT plus B e to minus 2T as your right guess. Any other guess won't work. You won't be able to match it up. Any question? So again, I don't think the book goes this far, but it's not that strange if you see this kind of example. So it's good that you understand, right, the principle behind this choice. Is that okay? Versus, let's say this for this case. And then again, right, versus this for this case. All right. So the last question. The last one I want to do, right? Again, we're still within 4.1, and 4.1 has a theme that, you know, the right-hand side, the forcing function is exponential. So I keep changing the left-hand side, keeping the right-hand side still exponential function. So in that sense, I guess I violate it a little bit here, but you know, I still think it's some exponential function-ish. Okay, let's say this, right? So here, right, the homogeneous solution is lambda squared plus lambda equal to 0. So lambda squared plus 1 is equal to 0. So lambda is plus minus I, right? So YH is C1 cosine T plus C2 sine T, right? So I guess it's pretty straightforward, right? YP is A e to a T, right? And solve for A. Solve for big A, right? So in this case, right, suppose I have a complex root. So you see what I was doing, right? This is complex root. This is repeated root, right? And this is two distinct roots, right? Two distinct roots. So with the complex root, and if the right-hand side is exponential, do I have any worry about any coincidence between my particular and my homogeneous solution? If the left-hand side, right, if the characteristic equation has complex root and the right-hand side has has exponential forcing function, is there any worry about coincidence between YT and YP and YH? Yeah, no, right? I mean, exactly that. So here in this case, right, when, right, the forcing function is e to alpha t, and right, the characteristic equation has complex roots, then there's no worry about coincidence, right, between YP and YH. Because one is real and one is complex, right? They cannot be equal to each other. All right. Question? So if not, I think it's a good place to stop. Have a good Thanksgiving, everyone. And I'll see you next week. Yeah, Kat, it's on the syllabus, right? Yeah, you too, Daniel. It's on the syllabus. It's posted, it's on the syllabus, and we follow the university. Yeah, thank you. Schedule. You too, thank you. Have a good Thanksgiving. You too.